with Mansi when she was a postdoc here. So kind of began my astronomy career here. So I'm very excited to be back and give you an update of what I have been doing in the past 5 years, or even more, 6, I think. So what I would like to talk to you today is about insights into stellar explosion that we can get by observing them in the infrared. And this talk will cover kind of phenomenologies of what kind of things you can observe in supernovae when you look at them in the infrared, both before and after the explosion, and also long before the explosion. And if I have time in the end, I will pitch the instrumentation project that I also work on. I spend kind of half equal amount of time on instrumentation and science, but today, unfortunately, I will only have time to focus on the science and the observations.
We think that the instruments are science.
Okay, yes. Yeah, unfortunately, the science that the instrument does, and also the instrument itself, is quite different from, from the main theme of the talk today. So most of the talk today is work done with Mansi, Kazuo, Ryan, Nathan Smith, Ori Fox, and the rest of the Spirit team. And Spirit was a collaboration that also started here. So in this beautiful picture of firework galaxy, NGC 6946, you will see a teeny tiny dot, which is the Supernova 2017 EAW here. And I will talk more about it later. So the goal of the talk today is to convince you that infrared is good and it is cool. It will tell you a lot of things about molecule and dust formation in supernovae. And what I want to try to convince you most is that infrared observations are not just good to look through the dust, as like a lot of people like to pitch, but there are a wealth of information that have actually not been well probed at all, just due to the lack of comprehensive observations like what we have in the optical. In this talk, I will focus on 2 nearby, very bright and very well observed supernovae. 2017 EAW, which was an explosion of a common red supergiant as a Type II supernova, and 2014 C, which is quite a peculiar explosion of a hydrogen-poor progenitor star that interact with its lost envelope. So all these explosions fit into the common picture of this stellar evolution, where we like to imagine a single blue star starting its life as a solar mass blue star, evolves off the main sequence into a red supergiant, do its own thing, finish its nuclear fusion in the core, and then explode as a core collapse supernova and produce supernova remnant. So this is quite a simple picture that, as more observations come in, we start to realize that it's, in the reality is not as simple. And this deviation from the simplistic reality comes in from the observation of these different flavors of core collapse supernovae. So if you look at core collapse supernovae, you will find that about 60-65% of them belong to this so-called Type II plateau. So Type II means that you have plenty of hydrogen at all phases of the light curve. And plateau means that the luminosity of this supernova remains roughly constant for about 100 days. So therefore, a plateau. And this plateau happens because when you have a very extended hydrogen envelope around the star, what happened is that after the initial explosion, all of the envelope is ionized. And as the ejector expands and cools, you have the front of hydrogen recombination at roughly constant temperature receding into an expanding ejector. So this recombination front remains at roughly the same distance at the same temperature for about 100 days. So you have a plateau for about 100 days. However, this ratio is kind of actually pretty small. Because of the typical IMF, you would expect that most of the massive stars that explode as supernova will explode with the hydrogen envelope intact. And the reason is because if your star evolves as a single star, the mass loss rate only goes up high enough to eject the whole hydrogen envelope if you begin with a star with 30 to 50 solar mass or more. Now we know from the IMF that we don't have that many very massive stars. So the problem arises when we look at the ratio of these so-called strip envelope supernovae. So these are type 1b and 1c. Type 1 means no hydrogen. 1c has signatures of helium, and 1b has signatures of helium, and 1c has no hydrogen, no helium. So my point here is that this fraction of a strip envelope supernova is too large for single star evolution to explain. Another kind of puzzle in this supernova flavor picture is the so-called interacting or 2N supernovae, which make about 10% of all core collapse supernovae. So in these interacting supernovae, the shock from the supernova runs into a very dense material that is present around the progenitor star. And again, if you have a single star evolution scenario, it's often difficult to produce this very dense shell around the progenitor star right before the explosion. So what process is responsible for stripping this whole entirety of hydrogen envelope out of about 30% of progenitor stars that explode in core collapse supernovae, and also kind of relatedly produce this 10% interacting, like strongly interacting supernovae. And I think to try to answer this question, we have to look into supernovae at late time as the shock interacts with more of this material around the progenitor star. So one clue that we already have about to answer this question is that is the realization in the past decade that most massive stars don't live alone, and they all have binary companion. And what's more is that they interact with their binary companion. And this paper from Hughes-Sana in 2012 showing that, in fact, only about 30% of all core collapse supernovae, about 30% of massive stars evolve like a single star. The rest of them are in the parameter space in binary configurations that would either strip the envelope, have a common envelope phase evolution, or even merge. And the picture on the right here is the ground-based observation, adaptive optics observation, combined with a HST image of a galactic star called RY Scuti. And this is one of the very few rare stars that have actually been imaged at very high resolution to show this complex circumstellar environment. And I will come back to this particular star later. Before going into 17EAW and 14C, I want to give a brief overview of what you can learn from infrared observations. And I think the two really important things is that, one, infrared observations can show you the formation and signatures of molecules in supernovae. So turns out most, if not all, type 2p and possibly also all type 1bc produce some kind of molecules in the ejector as the ejector cools. And this is actually really important because what I'm showing here is the series of spectra from 17EAW showing the formation of carbon monoxide. This is important because the formation of carbon monoxide does two things. One, it takes all the carbon and all the oxygen out of the ejector, and this formation actually sets what kind of species are left to produce dust later on. Another thing is that CO is a really, really, really good coolant. So in order for dust to have any chance to form in the ejector of supernova, you have to form carbon monoxide, which leads to the picture on the right, which is a thermal emission from dust. This can be dust that is pre-existing in the circumstellar environment, ejected by the progenitor star, or formed in the supernova, in the cooling ejector of the supernova itself. A lot of this work, as I mentioned, started here in 2014 with a survey called SPIRIT's Infrared Intensive Transient Survey. This is a large survey with spacer warm mission. We used 3.6 and 4.5 micron channels of spacer to look at all nearby galaxies. The goal for this survey is actually to find new and weird intermediate luminosity transient that only exists in the infrared, but don't show up at all in the optical. The survey produced quite a number of those, and you can read Mansi's paper or a paper from Jacob Jensen, another grad student in my group who recently graduated. And you can also talk to me afterward about all those weird and wonderful things. But my main role in this survey is to look at sites of actual known supernovae that are regular, detected in the optical, didn't have any crazy obscuration. Turns out we cover about 141 sites of those normal optically detected supernovae, and we produce a collage of all the light curves in 3.6 and 4.5 micron for all these core collapse supernovae. You can already start to see from here that most of them evolve as you would expect. It blows up, it peaks, and then fades away in roughly like a 1-year time scale as the dust cools. Now, you can already see from this collage of light curves that two supernovae kind of stand out. One is 2011 JA, which is type 2P with extra light from likely from circumstellar material interaction. And another one that I will talk about in details is 2014C, and this one you can see that is quite spectacular. Turned on in 2014 and is still pretty bright today. But before we get to 14C, I will talk about what infrared observations can tell us about a very common type 2P supernova. So 2017 EAW was not featured in the last figure because it exploded in 2017. And the last figure covers samples only up until early 2014. But this supernova is very important because it exploded very, very nearby. This was in NGC 6946, the well-known fireworks galaxy. If you work in transient or supernova or interested in these things in general, you know that this was the 10th supernova in this galaxy in the past century. So that's about 10 times the typical rate of core collapse supernova in spiral galaxy. And its location is kind of up here, and I'm showing two images from June 2017 and July, and you can see the supernova fading. Now, even though this supernova was not in original SPIRIT sample, it was in the SPIRIT's galaxy. So what that means is that we have a lot of pre-explosion observations, both from with spacer and from the ground. So this series of 4 images actually show the detection of the progenitor star to this supernova observed by Mossfire on Keck and work on the 200-inch telescope at Palomar. And you can see a clear detection of the progenitor star. In one of these epochs, we also have a JHK multiband photometry that shows like a SED you would expect from a red supergiant. But what I want to focus on is the fact that if you do photometry for all these 4 images, you see that the flux of the star didn't seem to change significantly at all over the course of 1 year before the explosion. Another interesting thing is that this last image from May 9th from Keck was actually taken within like a week before the explosion, and the explosion was, I think, first detected on like May 15th, and early light curve fitting actually put explosion date as May 10th.
Have you gone back more recently to make sure that goes away? Or is the supernova faded enough?
I don't think it faded enough yet. Yeah, but I will check that. And this result actually agrees with another result from optical survey. This is from the LBT survey that try to find like this disappearing star that just directly collapsed into a black hole without exploding. And they also cover NGC 6946 and have a 10-year baseline on this progenitor star to show that like basically nothing happened. So this is quite perplexing because it's telling us that like there's basically no way you can predict that a red supergiant is going to die. Although there are some other papers claiming that they find some variability as well, so you can look those up. Now, I said this is perplexing is because we actually have some evidence for really nearby circumstellar material around the progenitor to this supernova. One evidence of that comes as this high velocity absorption feature in the helium line in the infrared. So typically, when you have this expanding photosphere, what you have is a Preexplosion profile. You have emission from most of the shell, and then you have the absorption from the material that is coming at you, because that's the velocity coordinates that you have most opacity on. So typically, the line profile is like this. You have a emission peak, and then you have a Preexplosion absorption trough. Now, if you track the Preexplosion absorption trough for helium-1, you see this receding velocity, and the reason is because the recombination front for both hydrogen and helium are receding into a slower ejecta as time progresses through the plateau phase. So this is expected. But when you look at the series of spectra from this supernova, you also notice another feature that remains constant velocity at about 10,000 kilometers per second, which is the velocity of the fastest ejecta. And one scenario where this can happen is if, so scenario one up here is when you only have the recombination front. You just have a typical Preexplosion profile. But this scenario in the bottom is when the shock is actually running into some kind of dense wind that is lost from the progenitor star. And what happened is that high energy photons from that interaction can propagate back into the fastest moving ejecta and excite those material to the stage that can produce this absorption line. And unlike the recombination front that is receding into a slower ejecta as time progresses, this process keep ionizing always the fastest moving ejecta. So that's why we see a constant velocity in the absorption line. Another interesting thing about this supernova is that in 2004, there was another core cloud supernova in the same galaxy called 2004 ET. And it has a really interesting evolution in the infrared. This is 2004 ET, or this star. It fades for about 1,000 days, and then it jumps back up. And this supernova is actually still detected in Spitzer images. And this late time emission is likely coming from the shock eventually running into some very distant shell. And this is actually quite similar to what observed in 1987A, where you go back like 10 years later and the shock runs into this circumstellar ring. So the picture this is painting is that even for the common kind of vanilla flavor core collapse supernova type 2P, there's still a lot of circumstellar environment that we don't probe yet because we don't typically have observation at such late epochs. But yeah, for this supernova, it would be really good to try to keep tracking it and see if it will interact like O4ET. I'm switching gear now to a more extreme example of interaction of a supernova shock with its CSM. So this is 2014C. And the reason why this supernova is really odd is that it exploded in 2014 January just like a normal type 1b hydrogen poor supernova. The spectrum here is showing only like very small H alpha from the host galaxy, but most of it is just a typical 1b spectrum. The supernova went behind the sun, and then it came back on the other side with booming H alpha. That H alpha emission has been growing since, and I believe from talking with some colleagues who observed this in the optical, it's like that H alpha feature is still there today. So what happened is that we have this really rare scenario where a hydrogen poor progenitor star actually explodes in the cavity, and then the shock runs into the envelope that is lost from the star. This typically does not happen, and it seems like some either 14C is some lucky coincidence where the explosion actually happens when the material lost from the star is still like nearby enough for interaction to happen. So this is to show that this CSM interaction is very long-lasting. We have last observation from November 12th, so a few weeks ago, and you can still see this supernova in the host galaxy, like very, very strong. And for a spectroscopic evidence, we have observation not as late as this, but from 2018 in September. This is a spectrum from NIRES showing the line profile of the helium-1 line. And you can see this complicated multi-component structure, which probably means that the CSM itself is not like a smooth shell or a smooth ring, but has some clumpy components to it. So what's most exciting about this supernova is actually the fact that it's so bright and so nearby. We observe it at 10 micron with the COMEX instrument on Subaru. 10 micron is an important wavelength because it has this strong feature of silicate dust there. And we have just at 5 sigma detection, and if you look at the NOT images, you can see both positive and negative source. So this is real. You can trust me. And it looks slightly better on my laptop screen. This detection is very exciting because actually this is only the 4th interacting supernova that has ever been observed beyond 5 microns. And the reason is simply because the atmosphere is really difficult to deal with beyond even 3 microns. And Spitzer only has a few years of the Kaew mission that managed to observe 05 IP. And what you can see from this plot is that all the other interacting supernovae observed at this, like about 1,000 days post-explosion, all showed like no feature at 10 micron. That is interesting because if you look at galactic stars that we think produce these kind of interacting supernovae, so these are galactic stars with dense nebulae around them. If you take a spectrograph and point it at them, they pretty much all of them show this 10 micron emission feature from silicate dust. So the question has actually been like, are the extragalactic Type IIn supernovae coming from a totally different class of massive stars than the galactic massive stars we know have dense shell around them, like these LBVs, for example? Or is it just because the dust get destroyed, or is it because of the optical depth effect that don't show us emission features? But anyhow, we show with 2014C that at least some of the core collapse, some of the interacting core collapse supernovae do show this 10 micron feature. So with this IR-SED fitting, I still say submitted. It was accepted yesterday. It was published yesterday. It was accepted a while ago. But another thing that we did is we say, well, at this latest time, most of the emission come in the infrared. So we fit this SCD to a lot of the Spitzer observations we have and try to derive some like volumetric luminosity and try to fit it with a CSM interaction model, assuming some efficiency of interaction. And there are two things that we learned. One is that the density profile in this CSM is very similar to just a plain rho prop to r to the minus 2 like wind-driven profile. And this was slightly surprising because most of these dense CSM systems we think are ejected in some sort of like an eruptive event that would produce maybe a constant shell, or even if with the wind-driven profile, the extent of the CSM should be pretty limited. But in this case, we found that the CSM is actually, the geometry of the CSM is pretty much a very dense shell. And this is the shell that the supernova began interacting with like back in 2014. But from then on, it's basically a large, very extended wind-driven CSM profile. And from this, we try to compare it. This is a plot of mass loss rate you derive from the wind-driven profile and the expansion speed. And 2014C, the outside CSM fall kind of down here. And this is this phase space is plotted with like all the known massive galactic stars. And also these points show like all the previously observed interacting supernovae. And the idea is that like, you know, if O5 IY is here, is probably produced by LBB giant eruption as opposed to these guys who might be a binary mass loss. The interesting thing is that 14C seems to have all of them. And if you plot the inner bubble parameters, this is before the interaction started, the mass loss rate and the expansion velocity seems to be in agreement with some Wolf-Rayet star. At 100 days post-explosion, the shock runs into this kind of dense nearby shell. And that shell parameters is way up here in agreement with some sort of LBB eruptions or, yes, with LBB eruptions. And then if you wait a bit longer, a few more hundreds of days, the parameters kind of fall down to this binary Roche-Loeb overflow area of the parameter space. So we think this is like the first example of kind of like a more complete picture of what massive stars can do right before the explosion. That it can have some sort of long-lasting binary interaction phase where it produced this like hugely enhanced wind that is losing mass at like 10 to the minus 3 solar mass per year rate for quite an extended period of time to produce this outer CSM we find. And then it concluded with some sort of eruptive event that produced a dense inner shell. And then after that, it can have like really, really low mass loss rate for quite a while before it exploded. So this is quite a unique scenario. So I will, here. So the last thing I will talk about in this talk is that the system like 14C is, actually has quite a good galactic analog. And this is the star I showed earlier in the talk, RY Scuti. The similarity is quite striking in two ways. One is that the distance between the CSM you see here and the main star in the center is actually almost identical to the dense shell we found in 2014C. The distance is about 5 times 10 to the 16 centimeter, which is about 3,000 AU away from the star. Another similarity is that from old Keck data with back when Keck still has mid-infrared instrument, the observation also show the evidence of this 10 micron emission feature that I mentioned earlier that 14C had. So these are the two similarities between the two systems. The difference is that our Scudi actually, even with like this very clear and bright CSM around it, it only has like a really, really small mass in the CSM. The total gas mass was estimated to like 0.003 solar mass. In comparison, 14C, to be able to produce that much flux that lasts for as long as it did, the total mass in the CSM has to be in order of a few solar mass. So that's the main difference.
What is the spectral type of the star?
So our let's see. So our Scudi is a known binary system, and it is known because it's an eclipsing system. So I think the primary star is almost a Wolf Rayet. It had, like, most of the hydrogen envelope is already removed. And the secondary star, I believe, is like a late O. Yeah. And so that is also really interesting because of the fact that the primary star of our Scudi is stripped. If this were to explode today, it might look pretty similar to 14C. Maybe with a smaller amount of interaction because the amount of stuff around it is a lot lower, but it will look quite similar. Yeah, so there's a lot of exciting things to be done in the future. Infrared is just getting started. We are getting a lot more instruments coming online, hopefully on time. What I'm most excited by James Webb is the fact that we will now actually have a spectrum from like 1 all the way to 20 micron, like actual spectroscopy. So we no longer have to show like an SCD with 2 or 3 points and claim that we find this and that features and we fit this and that dust model to it. Like with the actual spectroscopy, you can actually apply dust models with realistic grain size distribution and geometry, and actually constrain, do a meaningful constraint to those parameters. And another thing you can get, I didn't have time to talk about that a lot today, but molecule and dust formation history in supernovae are actually like really poorly observed, because with Spitzer, it's really difficult to disentangle all these different aspects that go into the emission. So Webb would be very exciting. So the goal now is to write a compelling proposal and try to get some data on these Caltech supernovae with Webb. For W first, I think what it will contribute most is actually in the progenitor search for these nearby Caltech supernovae. So like 17 EAW was lucky because it's so nearby, and it so happened to have Hubble images before the explosion. But for the majority of even like very nearby Caltech supernovae, we never had high resolution Hubble images. So there's no chance of detecting the progenitor star. So I think that's the area where W first will contribute the most. So yeah, I'm still optimistic that it's still a 0 there. But anyway, I will leave out my conclusion up here and take any questions. Thank you.
So there was a recent black hole, like 70 solar mass black hole that we found, and they said that one of the ways to make it might be like a really low mass loss rate compared to like the stellar evolution models have. Do you know if given that the rate at which the mass loss is happening is changing and stuff, do you know if that effect like lowers what we think overall mass loss rates for these things are?
Yeah, so I think those cases are very rare, because if you end up with a 70 solar mass black hole, the initial star must have been several, probably like few hundred solar masses.
But their point is that you
Yeah, you somehow have.
You reduce the mass loss rate by a factor of a lot.
Right. Yeah, so I don't know that.
Well, sure,
Right.
but
Yeah.
I guess like compared to what usual mass loss rates are, how does what we learned from 2014 compare for like the integrated over the whole?
So is my best guess would be that these are like very different populations. Yeah. So another thing I didn't mention about 14C is that the ejector mass is measured to be like really low. So this is actually another. So in addition to the fact that there are way too many strip envelope supernovae, another evidence that these strip envelope supernovae come from binary interaction is actually from Maria Drau's work that show that most of them have only like very few, like 1 or 2 solar mass, ejector mass. So the progenitor couldn't have been very massive. Yeah. So with actually with stars like that large in mass initially, I think a lot of models predict that they don't explode at all. It just directly collapse into black holes.
So when you were talking about molecule formation, you showed a late-time K-band spectrum with a very strong CO line.
Yes.
389 days. And 20 days later, it's totally gone.
Yeah, yes. I'm so glad you caught that. So this is another exciting thing about 17AW that I didn't get to talk about, which was the formation of carbon monoxide. And this evolution is actually like very similar to what observed in 1987A. And my initial reaction seeing this is that I first thought that it's because the shock is overrunning the CO forming area and destroy all the CO. But that turned out not to be the case. And the reason is because if you look at the Spitzer light curve, the 4.5 micron is still really bright. And turned out that it's because the fundamental transition is still let's see, how do I phrase this? So basically what happened here is that the excitation temperature is dropping just low enough that this overtone transition don't happen anymore. Yeah, I think the transition temperature is around like 2,000 Kelvin, maybe a bit lower, maybe more like 1,200 actually. So one great thing that this can provide is actually a really, really precise and strong constraint on temperature of the ejector at the time, because like even just with 50 or 100 Kelvin difference, the line profile changed like dramatically. Yeah. So this is basically just a temperature effect. Another thing working on this supernova show is that actually like all the work trying to fit Spitzer warm Spitzer data to try to get mass, which is basically what I did in my 2016 paper, can be quite misleading because a lot of the 4.5 micron flux come all from CO. Yeah. Initially, I guess people don't realize how strong the effect that is.
So have you guys looked in the spirits data at any kind of young supernova remnants, supernovae that have been 10 or 20 years earlier? We have data for them. What kind of things you would look for? I don't know. I'm just curious what you might see in the infrared at those kind of stages. I would think they would still be pretty bright, but I don't know what the other.
Yeah, so most of them we don't detect anything, but we actually detect like super late time emissions from these like well-known radio supernovae, and also like for example 93J, we still have like a declining light curve from like early 2010s, and in my 2017, in my 2016 papers, I listed, I think, like 5 supernovae that are detected like after 2 or 3 decades post-explosion. So 93J was one of them. And I would predict that 14C would be another one. And yeah, one thing I have a data and I'm trying to find time to work more on it is actually O4ET, because we still detect this like declining light curve from after that secondary peak in at like 1,000 days post-explosion is still like continuing to decline. The problem is that we only have detection in one band, only in 4.5. So any attempt to do like a bolometric luminosity will be questionable at best. Thank you so much.